Now that we have the definition of variance and standard deviation, let's use them. These definitions depend on the probability density function of our continuous random variable. This probability density function we've already dealt with. We know its expected value. Let's recall the definition of variance. It's the average distance from the average. So in order to compute an average, I take the thing I'm averaging times my probability density function. So this is going to be the expectation of whatever is in those brackets. Now what goes in those brackets? I'm going to take kind of my measure of surprise. So that's my value minus my expected value. And I'm going to square it. This is going to get rid of any information about whether it's too high or too low. In our case, my expected value, we computed this in a previous video, is 2/3. And now in order to fill in my probability density function, I need to turn this piecewise. So I know from -infinity to 0, this is going to be 0, because my probability density function is 0 on that interval. Then I need to compute what's going on when x is between 0 and 1. The thing I'm averaging is my surprise squared, x minus expected value of x squared. On this interval, my probability density function is 2x. And then finally, on the interval from 1 to infinity, my probability density function is 0. So the contribution here is just going to be 0. This tells me the antiderivative that I need to compute is 2x times x squared minus 4/3 x plus 4/9. Distributing that through, here is the polynomial that we need to antidifferentiate. And I'm going to evaluate it from 0 to 1. The 0 case is easy. The 1 case is 1/2 minus 8/9 plus 4/9. So this is 1/2 minus 4/9, which is 9 minus 8 over 18, which is 1/18. So the variance of this continuous random variable is 1/18. When we define variance, we said there's actually an equivalent definition. So just to show you how to use that, let's recompute the variance. We still have to get 1/18. These need to be the same, but this is a different way of computing. And order of operations becomes very important here. The expected value just of x is 2/3. So this second term here is just 2/3 squared. The thing we have to worry about is this first term here. But we can start just with the definition of expectation for that first term. So the definition of expectation is -infinity to infinity of my value, which in this case is x squared, times my probability density function, f of x. The expectation of x is 2/3, and I just square that for my second value. As we've seen before, in this particular case, because our probability density function is 0 outside of the interval from 0 to 1, I can replace this with a bunch of zeros and then the integral in the interesting part. So instead of considering everything from -infinity to infinity, the non-zero bit is between 0 and 1. And on that interval, my probability density function is 2x. So what I need to compute is the area under the curve from 0 to 1 of 2x cubed, and then that whole thing minus 4/9. So that new integral I had to compute was 1/2. That's the expectation of x squared. So what that means is I do my random process, I get some value, and then I square it. And so instead of averaging the values, I average the squares of the values. And this ends up being different from just taking the average and squaring it. So if I take every value and square it, then take the average, I get a half. Now a half minus 4/9 is 9/18 minus 8/18, which is 1/18, which is what we got before, so we did it correctly. Now that I have the variance, it's trivial to find the standard deviation. So to compute the variance, remember we had to take the actual value minus our expected value, but then we squared it. And so that gave us values in a weird range. So to kind of compensate for that, the standard deviation is nothing but the square root of the variance. So let's go over the interpretations one last time. Expected value is like an average. So I have some event, I run it again and again and again, record the value every time, take the average. If I did this a bunch of times, the average should be pretty close to 2/3. So I say, okay, the average should be 2/3. So I run the event a bunch of times, and it's not always exactly 2/3. So every time I run the event, I figure out how far it is from 2/3, how far it is from the average. Then I take those differences and square them in order to destroy any new information about whether they're positive or negative. Average that, get about 1/18. And then if I take the square root of 1/18, that is my standard deviation. That's 1/3 √2.